Hello, and welcome to Astronomy 121's tutorial on the fundamentals of astrophysics. In this lecture, we'll be covering some basic astronautical concepts that are frequently used in the course. These include the celestial sphere, parallax, the inverse square law for radiation, and the Doppler shifting of light. These topics may seem highly disparate, and indeed they are, but it turns out that they all have something to do with measuring astrophysical quantities of interest. Since we'll be covering many topics, I'll be interspersing examples throughout the lecture. Let's start with the celestial sphere. When we look up at the night sky with our eyes, we don't get a sense of how far away things are from us. It therefore might be tempting to say that all the stars are the same distance from the Earth, forming a great spherical shell with the Earth at its center. This celestial sphere concept was adopted by a number of ancient cultures, for example, forming the basis of the Greek geocentric model of the universe. Those models had more complicated treatments for the planets and the sun because they didn't move like the rest of the stars did, but the same idea applied to them too. Today we know this concept is wrong, as the Earth isn't the center of the universe. But, like the constellations, it can still be a useful tool for navigation and determining the angular position, where in the sky, an object is. In this course, we don't really use the celestial sphere, but we do use the geometry associated with the celestial sphere. Suppose you're standing on the surface of the Earth, right over here. The zenith of the celestial sphere is defined as straight up from your perspective. And how high in the sky an object is can be described by an angle between the object and zenith. So for example, the moon here, this angle here describes how high the moon is from the sky. Alternatively, we can describe the angle between the ground and the object as how high it is in the sky. And that's just because the ground and zenith make a 90-degree angle. A second angle corresponding to the horizontal position of the object would completely define the object's position in your night sky. This isn't particularly useful for astronomers in other parts of the world, since their zenith would be different from yours. For example, the zenith of the North Pole, straight up over here, would be parallel to this line, while straight up on the equator would be a line somewhere in this turquoise disk. We need another system that anyone on Earth can use. And so we do this by reflecting the latitude-longitude system of the Earth onto the sky. The North Pole zenith maps eventually onto the North Celestial Pole, the South Pole onto the South Celestial Pole. Some line on the equator eventually goes onto this circle here, and if you map enough of these zeniths onto the celestial sphere, you get what's called the celestial equator. We can then define a latitude and longitude, called a right ascension and declination, in the sky that describes the position of any object. Note that the spin of the Earth is not taken into account in this system. This is so that the right ascension of an object doesn't change over the course of a single night. The Earth is tilted with respect to the plane of its orbit, which means that using this system, the Sun has a different declination at different times of the year. On June 21st, the summer solstice, the Sun is here, and has a declination of positive 23 degrees, where positive means above the equatorial plane and negative means below. On the winter solstice, December 21st, the Sun is here and is 23 degrees below the equator. Halfway through, the Sun is at zero declination, and these are known as the vernal and autumnal equinoxes, when the nights and days are equally long. We don't really need the details of the system, but the geometry is useful for answering questions like the following. How high and how low in the sky does the Sun get at Yellowknife, Northwest Territories, which is a latitude 62 degrees north, which means 62 degrees above the equator? To solve this problem, we go to the diagram. This diagram is oriented slightly differently than the ones we saw earlier, in that the Sun-Earth plane, parallel to the direction of sunlight, is horizontal, while the equator is tilted. On the left is the diagram during the summer solstice, when the Sun has the most positive declination, while on the right is the winter solstice, when the Sun has the most negative declination. These will be the extrema of the Sun's position on the Yellowknife sky, and if you don't believe me, try drawing the Earth-Sun system, this diagram basically, at other times of the year. Latitude is defined as the angle between the equator, the center of the Earth, and Yellowknife. So in this diagram, this angle here, and this angle here in this diagram. And that value is 62 degrees in our case. Since Yellowknife's zenith is straight up at Yellowknife's position, the zenith line is just this line here. and this line here in this diagram. On the summer solstice, the angle between the equator and the incoming sunlight is 23 degrees, this angle here. And the angle between Yellowknife's zenith and the equator is, as usual, 62 degrees. So the angle between Yellowknife's zenith and the sun is 39 degrees. That's this angle here. Or, the sun gets 51 degrees above the horizon. On the winter solstice, the angle between the equator and incoming sunlight is 23 degrees again. But the sun is below the equator, so the angle between Yellowknife's zenith and the sun is 85 degrees. And the sun only peaks 5 degrees above the horizon on the winter solstice. We figured out a way of describing the position of an object on the sky, but we still have no idea how far away things are. To answer that, we turn to our other two topics, parallax and the inverse square law. Let's start by describing some basic trigonometry. Take this right triangle with height L and base D. Basic trig gives us the angle theta from the tangent. This equation here, tan theta is equal to L over D. But if L is much smaller than D, then tan theta is approximately equal to theta, and we get the small angle formula, theta is equal to L over D. Now, this geometry is identical to the geometry of an observer observing a distant object if the height L describes the height of that object, and base D is the separation between the observer here and the object. In that case, theta is the angular size of the object, commonly given either in units of radians, or degrees, or arcseconds, where 1 arcsecond is 1 over 3,600 of a degree. We can extend this to 2 dimensions. Take an object of length L and width W. We can construct identical triangles as we did in the previous diagram for both L and W, and from that obtain angles theta L and theta W. Now theta L times theta W is equal to omega, which is called the angular area. This has units of steradians, square radians essentially, square degrees, or square arcseconds. Note that if L and W are not small, this picture gets a lot more complicated. Let's look at one more situation. Suppose we're on the Earth here, and we're observing this star here. So we look along this line of sight here. We then wait 3 months, and we do it again, in which case our line of sight is along this direction here. Now, because we have moved positions, we'll notice that the star has shifted against the background of much more distant objects. Technically, they'll move too, but the movement is negligible. Now, if we draw the geometry of this system, connecting the Earth, the Sun, and the star, like so, we find that the geometry is identical to the triangle we had a few slides back. We therefore can use a small angle formula to calculate L, D, or theta from the other two values. In this particular case, we know L well. It's just 1 AU, the Earth-Sun distance. Theta we know as well because we can determine it based on the shifting of this star in comparison to background objects. We therefore can calculate D, and this is what allows us to calculate the distances to very distant astronomical objects. Now it turns out that if we use L in astronomical units and theta in arcseconds, then D will be in parsecs. This is in fact how parsecs are defined. Note that generally we wait 6 months so that our L, our baseline, is equal to 2 AU rather than 1. From equation 2, you should see that this gives a bigger angle for any given D. Bigger angles are easier to see, try this with your own eyes, making it easier to determine larger distances. Let's do a quick example. Suppose we take 2 measurements of Proxima Centauri, the nearest star to our own sun. These measurements are taken 6 months apart, giving us a baseline of 2 AU, and we see Proxima Centauri drift by 1.53 arcseconds. How far is Proxima Centauri from the sun? Well, if we use equation 2 from the previous slide, 2 astronomical units divided by 1.53 arcseconds is equal to 1.31 parsecs, or 4.27 light years. This is the closest star to our sun, so one can imagine that more distant objects, hundreds of light years away, will require much more precise measurements. Next, let's talk about the inverse square law of radiation. An object emitting light has a luminosity, defined as the total energy it's outputting per unit time. For black bodies, this is simply luminosity is equal to the surface area of the object times Stefan-Boltzmann constant times temperature to the 4th power. We can imagine that the light emitted in 1 second as an outgoing spherical shell of photons, like this. from the source in the center here. In general, the amount of light emitted in one direction won't be the same as the amount emitted in another, but let's assume that it is. In the case of stars, this is a good assumption, but in the case of planets, it isn't, because planets reflect a lot of light from their parent stars. In this case, the radiation is said to be isotropic, meaning spherically symmetric. Due to conservation of energy, the energy contained in this shell is always constant. We now define flux as the radiation received per unit area. The average flux is just the luminosity divided by the surface area of the spherical shell. And due to spherical symmetry, the average flux is the flux anywhere on the shell. So we get equation 3, which says that the flux is inversely proportional to the radius of the spherical shell. This is important because our detectors, including our eyes, measure flux, not luminosity. So given an object of the same luminosity that's further away, it'll appear fainter. If we don't assume spherical symmetry, we have to do an integral, like so. But we get a very similar generalized version of the inverse square law. You may be wondering if there's some deep philosophical reason why many of the forces of the universe also obey the inverse square law, such as gravity and electromagnetism. There is one, in fact. It's all because they obey an equation similar to this one. See the inverse square law hyperphysics link in further reading. The inverse square law can also be used to determine astronomical distances if we know the luminosity of the emitting object. This is often impossible, but there are a class of objects known as standard candles for which the luminosity is known. We can determine distances to these objects, often much further than we'd be able to do with parallax. As an example, consider a Cepheid variable, a kind of standard candle star in a nearby galaxy. This particular kind of Cepheid, there's many, is known to be 20 times the solar luminosity. Our telescopes record a flux of 6.35 times 10 to the minus 19 watts per meter squared. How far away is the Cepheid, and in fact, the galaxy? Well, the star's luminosity is 7.6 times 10 to the 27 watts, since it's 20 times solar luminosity. If we rearrange equation 3, we get that the distance is equal to the square root of the luminosity divided by 4 pi times the flux. Plugging in numbers, we obtain 3.09 times 10 to the 22 meters, or 1 megaparsec. Note that this is a very hard measurement to make in reality, because 1 megaparsec is very, very far away for our telescopes. Lastly, let's turn to the Doppler effect. Doppler shift is a change in the frequency of emitted radiation due to relative motion between an object and an observer, and a constant radiation propagation speed in the medium. Doppler shift is commonly talked about with respect to sound and light. For sound, it's because sound waves have constant speed relative to the medium they're traveling through, like air and water. For light, speed is always constant. You can find the mathematical derivation for the Doppler effect in any first-year physics textbook. For a qualitative explanation of why the Doppler effect occurs, let's look at the above figure. On the left, we have a stationary car emitting sound waves, and on the right, we have a moving car emitting sound waves. Each one of these crests, when emitted, travels with the velocity of the speed of sound toward the observer over here. And they all travel in this left picture, where the source is at rest, the same distance. The distance from the car here to the observer. So they take the same amount of time to get there. And when they get there, the observer can time these crests of the sound waves that determine the frequency of the sound waves. Now let's consider the picture on the right, where the source is in motion. In this case, the first sound wave crest was emitted when the car was here, and it travels outward with constant speed to the observer over here. Subsequent sound waves, however, are not emitted at this point anymore. They're emitted as the car moves this way. So each subsequent sound wave has less distance to travel before reaching the observer. And effectively, the observer will see these crests coming in at shorter intervals, meaning a higher frequency. And this is the essence of Doppler shift. If the car was moving the other way, the reverse effect would occur. And if the observer, this person, were moving back and forth, the diagram would be different, but the overall concept would be identical. Now, Doppler shift obeys equation 4, over here, where lambda 0 is the rest wavelength of the radiation, meaning the wavelength if the object wasn't moving. For light, equation 4 works when the velocity, v, is much, much less than the speed of light. To see how Doppler shift is useful in astronomy, let's consider this slightly more complicated example. The Cepheid from the previous question was part of a collection of stars moving around a galaxy. so that's orbiting the center of the galaxy. This collection of stars is situated 34.3 arc-minutes away from the galactic center. The H-alpha absorption line at 6562 angstroms in the Cepheid spectrum is shifted by 203 angstroms, where 1 angstrom is equal to 10 to the minus 10 meters. How far away from the galactic center is the collection of stars orbiting, and how much mass is enclosed within the radius of the orbit? You can assume that the mass is spherically distributed within this orbit, and that the collection of stars is orbiting with uniform circular motion around the galactic center. Let's first determine the distance between the collection of stars and the galactic center. From the last question, we found the Cepheid, and therefore the galaxy, more or less, was 1 megaparsec away. 34.3 arc-minutes is equal to 0.01 radians, and through the use of the small angle formula, 0.01 radians times 1 megaparsec gives us 10 kiloparsecs, or 3.09 times 10 to the 20 meters. And that is the star-galactic center distance. To determine the enclosed mass, we must first determine how fast the collection of stars is orbiting. From equation 4, the Doppler shift equation, we get V is equal to c times the change in wavelength of the absorption line, divided by the rest wavelength of the absorption line. If we plug in numbers from the question, we get V is equal to 9.28 times 10 to the 6 meters per second. We then note that if we equate uniform circular motion to the universal law of gravitation, we get this expression over here, which we can turn into this expression over here. We have all of the values on the right because we just calculated them, so we can plug in velocity and radius to get that the enclosed mass is about 4 times 10 to the 44 kilograms, or about 2 times 10 to the 11 solar masses. If we integrated the light from inside of the orbit and applied a mass-to-light ratio, like what's done in one of the questions on your assignments, we could determine the fraction of M enclosed due to dark matter. Lastly, I've enclosed several links for further reading. If you go to Portal, you'll find the uploaded PDF of this lecture, and you'll be able to click on these links directly. Thanks for watching, everyone.